Hello everyone, I'm Robert An, a PhD student at UT Dallas. Today, we'll present our work discovering business problems using problem hypotheses, a goal-oriented and machine learning-based approach. Co-authors of this work are Ronaldo, Tom, Lawrence, Sam, and Lipping. Albert Einstein said, the mere formulation of problem is often far more essential than its solution. Here, he emphasized the importance of problem formulation. Our work is similar in that our focus is on problems and problem hypotheses. Please note that we present some updated work after we submit our final version of this paper. Okay. Here is the agenda. First, we'll introduce motivation for our work. Then next, we'll present Metis Plus framework for discovery of business problems. Then discussion and conclusion will be presented. Here's some machine learning challenge first. New technologies are collecting more data than ever before. Business organizations are investing big data and machine learning projects. However, most of these projects are predicted to fail. Some research suggested one of the key obstacles is lack of understanding of how to use data analytics to improve business value. It's challenging work to appropriately use and deploy machine learning to solve real business problems. In the bank world, for example, customer default, where customers fail to make timely payments, such as loan payment, might be a problem. Suppose bank managers have only vague ideas of which loan contract would be problematic. For this issue, we can consider the following questions. What would be the causes of this potential problem? How could the bank identify the causes behind causes? How could the bank validate the root causes? Would customer data such as account or transactions be useful for finding the root causes of this problem? Here's the problem statement. It is not easy to discover and validate business problems. Specifically, first, there are lack of systematic method to discover business problems hidden in big data. Second, it's not easy to figure out what data would correspond to problems. Third, it's not easy to understand how much data would impact the problems. Lastly, difficult in validating the problems. We noticed that bridging the gap between analysis of business problems and big data analytics is critical to answer the above research problems. Can a goal-oriented and machine learning-based approach help discover business problems? If yes, the next question is how? To help explore and discover business problems hidden in big data, we present the Metis Plus framework. The Metis Plus is illustrated with unpaid long case study. The Metis Plus framework is a goal-oriented framework that validates problem hypotheses using supervised machine learning. Metis Plus extends our previous work, Metis. It consists of the following four components. First, Metis Plus ontology, or modeling concept. Second, the Metis Plus process. Third, semantic reasoning methods. We define formal methods for validation of problem hypotheses. Fourth, domain-specific ontology. We'll describe this component in detail in the following slides. Here is the Metis Plus ontology, or modeling concept. Some key concepts of Metis Plus are soft goals, problems, problem hypothesis, machine learning, and data features. Key relationships are contribution, validated, or invalidated to. In Metis Plus, a soft goal is defined as a goal that may not have a clear-cut criterion. A problem is defined as a phenomena that negatively contribute to goals. A problem hypothesis is a hypothesis about a problem that need to be validated or invalidated using machine learning. There are two kinds of problem hypotheses. Those are an abstract problem hypothesis and testable problem hypothesis, where testable problem hypotheses need to be mapped to data features in a data set. Here is one use of Metis Plus modeling concept. In this diagram, a bank has a goal of increased personal loan revenue. This can be modeled as an instance of a goal. However, please look at the middle part of this diagram. However, customers' unpaid loan could be a problem to achieve the goal. Customers' unpaid loan can be modeled as an instance of problem hypothesis. Here, the low account balance after loan might be a potential problem, root cause problem that leads to customer unpaid loan. Low account balance after loan is modeled as an instance of the problem hypothesis. In modeling goals and problem hypotheses in customers' unpaid loan, we use Metis Plus modeling concept and relationship in meta classes, and token level. If the problem hypothesis is validated using machine learning in later parts, then it becomes a problem. Next, the Metis process includes 4 steps. Each step gets input and produces output. Step 1 is explore problem hypothesis in the context of business goals. Step 2 is identify existing data. We prepare a machine learning data set here relevant to problem hypothesis. Step 3 is evaluate problem hypothesis. In this step, use machine learning and Metis Plus reasoning method to evaluate problem hypotheses. Step 4 is validate problem hypotheses. Detailed sub-steps will be explained in the following slides. To illustrate Metis Plus framework, we use PKDD’99 Financial Data Set in the case study, where the bank offers client services such as opening accounts, offering loans, and issuing credit cards. The bank stores client transactions, loan payments, order payments, district, and other data in a database. In the loan table, there are 682 loan contracts. 606 loans were finished without problems. However, there were 76 unpaid loans. To discover potential problems concerning unpaid loans, we apply the Metis Plus process. Step 1 is explore problem hypothesis. Suppose the bank's high-level business goal is increased profitability. This goal can be decomposed to non-functional soft goal by and/or contribution link. Next, this non-functional soft goal can be further decomposed, operationalizing soft goals. For example, increase personal loan revenue. In step 1.2, then we consider potential problems that might negatively contribute to the goal. In other words, in the context of captured business goals, we explore potential problems. Here, in this graph, we consider the unpaid loan problem hypothesis. Like the goal refinement, we can refine the unpaid loan problem hypothesis to testable problem hypothesis. Here we show the partial problem hypothesis. Some problem hypotheses include low balance in an account and minimum balance for 3 months after loan. In refining problem hypotheses, we reviewed the banking ontology, financial database schema and data set, and interviewed with the bank staff. Next, step 2 is identify existing data. Based on the analyzed problem hypothesis in step 1, we prepare and build a machine learning data set. Step 2 includes 3 sub-steps. We explain each step in the next slide. In step 2.1, we identify operational features and a criterion of each problem hypothesis that was explored in step 1. Let's consider one problem hypothesis. Low balance in customer account might contribute to unpaid loan. First, there could be different ideas about low balance in an account. For example, we can consider the low balance in a checking account, low balance in a checking account and savings account or credit account. After we communicate the bank step, we use a checking account as operational criteria. And then we select a balance as the operational feature. Next, we model the problem hypothesis as class in UML. Step 2.2 is operational features to data features. For this mapping, we compare low balance class of the problem hypothesis and entities in the financial database schema with a cosine similarity. Next, we evaluate the ranked entities and data features using qualitative methods. In this step, we select the balance data feature in transaction entity for the low balance in an account problem hypothesis. Please note that the balance feature is in transaction entity, not account entity. Step 2.3 is extract a dataset using database query. We build a database query with the identified features and a target label. In the unpaid loan example, here the target label is loan status in the loan table. We may use join, groupify, or other ETL operations. Then we run the query and save the extracted dataset in a temporary space. And in C, we merge the saved dataset into a machine learning dataset. After this step, we get a machine learning dataset. Step 3 is evaluate problem hypothesis. For the extracted dataset in step 2, this step evaluates important degree of a problem hypothesis. In step 3.1, first we test a supervised prediction model for the paid unpaid loan. Then we select a supervised prediction model showing the best accuracy. Here we set up the model's accuracy criteria, for example 0.9, to get more accurate prediction models. In our experiment, XGBoost showed the best accuracy among the largest regression, decision tree, random forest. And the XGBoost passed the criteria. Next, we build an explainability model. We apply the sham model, which gives intuitive and consistent feature value. In step 3.2, we detect feature importance, which has a sign and contribution weight. In our experiment, the shape explainability model provides feature importance for the XGBoost model. This graph shows feature importance for one unpaid loan. This one shows feature importance for all unpaid loans. Here, for all unpaid loans, we can see that the following features positively contribute to the unpaid loan. Here, minimum balance for 3 months after loan, minimum balance for 3 months before loan, order count. Whereas average balance for 1 month after loan feature negatively contributed to the unpaid loan. After we get feature importance for each feature, in step 3.3, we update a contribution weight and contribution type of a problem hypothesis, where we apply the Metis plus semantic reasoning method. For the hypothesis P1 here, minimum balance for 3 months after loan in the right side graph, feature importance value I1 is plus 4.15. So P1's contribution type becomes S plus or sum plus. using the formula. And in step 3.4, lastly, we calculate the important degree of problem hypothesis. Here, the degree of P1 becomes 0.83 using score calculation formula. In step 4, we validate problem hypothesis. Okay, this is a big picture. We select best accurate classification model, here XGBoost, and we need to pass the criteria 0.9, and then we validate problem hypothesis. In step 4.1, we select the most accurate source problem hypothesis towards a target problem hypothesis. Here for the accuracy goal, low balance among the source problem hypothesis, we select accuracy goal minimum balance for 3 months. Here, please note that a validate problem hypothesis becomes a problem. We consider this problem hypothesis likely a root code problem. And in step 4.2, then we label the labels of other interrelated problem hypotheses and goals are evaluated using the qualitative reasoning method in bottom-up approach. More detailed description of this work can be found in our previous work, Metis. Okay. Next, we present rate work observation limitations of our work. Concerning rate work, some problem analysis techniques such as fishbone, pole tree diagram are helpful for exploring possible causes of problem. However, these techniques do not support for partial, full, positive, or negative contribution. Also, machine learning and problem hypothesis concepts are not supported in these techniques. On the other hand, machine learning is very good at performing predictions from large data sets and finding underlying patterns. However, machine learning is weak in supporting conceptual modeling for potential problem analysis. We feel that the Metis Plus framework fills this gap. Metis Plus bridges this gap with an end-to-end, explicit, and formal approach, providing traceability among business goals, problems, problem hypothesis, machine learning, and big data. Here are some observations. We observed that structuring a problem hypothesis as a class helps to identify relevant entities and features in a database. Here we use information retrieval approach. Otherwise, a priori ontology may be needed, which may not be available or need some time-consuming work in real-world applications. In addition, we noticed that mapping a problem hypothesis to data features using such approach, information retrieval approach, helps catch features in an unexpected entity. In the previous slide, transaction entity included balance features. Here are limitations and research challenge. One limitation of our work is that although explainability models, except shape, were not compared to get feature importance yet. Evaluating other explainability models with trade-off analysis would provide more rationale in applying the selected model. One research challenge includes studying utility of quality properties of supervised machine learning for the evaluation of problem hypotheses. For example, utilizing false positive, false negative seems to be useful for the evaluation of problem hypotheses. Here are the conclusion and future work. In this paper, we presented Metis Plus framework that uses machine learning and goal-oriented approach to help discover business problems by validating problem hypotheses. We believe that this work is one of the first to propose problem analysis using problem hypotheses. Here, 3 technical contributions have been presented. First, the refined Metis plus ontology and process. Second, a mapping method to data features. Lastly, a preliminary data extraction method for machine learning processing. Here is future work. We plan to explore more machine learning explainability models. And we also plan to do in-depth study about relationship between problem hypotheses and quality properties of supervised machine learning. Okay, this is the last slide. Thank you very much for your attention. If you have any questions or comments, please let me know. Thank you.